Hi, I'm Lewis. On behalf of my colleagues Liam and Christine, I'm happy to present our work on composing verification of foreign functions with Cogent. Before I get into the details of the work, I'd like to give a bit of motivation. Programs should be correct, fast, and efficient, and we should be able to implement and prove that they are correct without having to go to extreme efforts. Depending on the program, we may find that we cannot implement them as efficiently or even at all because the programming language we want to use might not be designed for that purpose. This is especially prominent for larger and more complex systems. To combat this, we can implement each component of a program in a different language suitable for that component. However, this introduces another issue: how to recombine these components safely, and how to compose correctness of each component to guarantee correctness for the whole program. When components may be written in languages of different levels of expressivity, safety, and precision of typing. In this paper, we provide a case study of a principal foreign function interface between a high-level language with strong static guarantees, Cogent, and a lower-level imperative unsafe language, C. We demonstrate that this foreign function interface still maintains the strong static guarantees for the Cogent components of a program, and that we can compose the correctness and safety theorems of the Cogent and C components to guarantee the correctness and safety for the whole program. Now for some context. Cogent is a high-level language that is purely functional and supports polymorphism. It utilizes a uniqueness type system to guarantee memory safety and allow for destructive updates of heap objects by enforcing that mutable heap objects only have one active pointer at any one time. Cogent is purposefully restricted. For example, it lacks recursion to enforce totality. To overcome these restrictions, programmers can import functions and data structures through Cogent's foreign function interface. These functions and data structures are written in template C, which is a special dialect of C that can refer to Cogent functions and data types. Template C code is compiled into standard C when the Cogent program is compiled. The expected workflow when using the Cogent-C system is that the Cogent components and the template C components of the program are compiled by the Cogent compiler into standard C. The compiler also generates a shallow embedding of the Cogent component and proofs that the Cogent shallow embedding is refined by its corresponding C code and that it is memory safe, assuming that the shallow embedding of the template C code is refined by its corresponding C code and is also memory safe. The functional correctness proof of the Cogent code and the refinement, memory safety, and functional correctness proof of the template C code all need to be manually proved. The functional correctness specification and the shallow embedding of the template C code also need to be manually defined. All embeddings and proofs are defined and proved in Isabelle Hull. To safely import C data structures and functions, Cogent enforces several proof requirements. These can be split up into three main requirements. Foreign functions must refine their shallow embedding and realistically their functional correctness specifications as well. They must also preserve typing, that is, if given well-typed arguments, they should return well-typed values. And they must be memory safe. To prove that these requirements are met in our particular context, we need to prove the following steps. To prove refinement for foreign functions in such a way that it can be utilized by Cogent, we need to understand how Cogent proves refinement. The Cogent compiler proves refinement in several phases, where each phase handles one main task. The shallow to polymorphic value phase shifts from shallow to deep. The polymorphic to monomorphic phase handles monomorphization. The value to update phase handles the introduction of the heap. The update to C phase handles the shift from functional to imperative. Note that the semantics in the gray rectangle are in Cogent's deep semantics. Each of the intermediate refinement proofs that the Cogent compiler produces assume that each foreign function also has a similar refinement proof. This means that we must define embeddings for each semantic level for each foreign function and data type. Relations between each semantic layer relating embeddings of foreign data types, and the refinement proofs between each semantic layer. While this may seem like a lot of extra work, the embeddings are essentially wrappings of Isabelle terms and relations, and the refinement proof is just the refinement from shallow to C, broken up into smaller steps. To prove type preservation for a foreign function, we need to know how to type any foreign data type it may use. The typing judgments take the following form. In the value semantics, this judgment only takes two inputs, a value v and a type tau. In the update semantics, this judgment takes a value u, a heap mu, a read-only heap footprint r, a mutable heap footprint w, and a type tau. While proof engineers are free to supply their own typing judgments for foreign data types, these need to satisfy several typing constraints so that they do not invalidate Cogent's uniqueness type invariant. For brevity, we only display the typing constraints for the update semantics, but similar typing constraints, where applicable, are required for the value semantics. These essentially state that when made read-only, the value should have no mutable references within it. There should be no internal aliasing or writable references by read-only references. All references should point to something, and values should remain the same if they are not modified. To prove that a foreign function is memory safe, we need to show that they satisfy Cogent's frame constraints. These constraints essentially state that memory should remain the same unless permission has been granted to modify it. Functions cannot leak any memory, nor can they allocate to a pointer that is already pointing to something. In this work, we have proved that the foreign function interface requirements hold for arrays and its operations length, get, put, fold, and map accumulate, which are all part of Cogent's standard library. We have used these proofs to discharge assumptions for arrays for previous file system verification work. And based on our experience with arrays, we implemented a higher order general loop iterator called repeat. That is essentially a for loop that repeats an expression either until the given counter reaches 0, or if it has been signaled to terminate earlier. We have verified that it satisfies the foreign function interface requirements and have used it to implement binary search, which we then prove functional correctness of. Both the arrays and general loop iterator allow Cogent to overcome its inability to store data in a single block of memory and to do iteration. Composing correctness and safety theorems of foreign C functions with Cogent functions is fairly straightforward. We demonstrate this by describing how to implement binary search in Cogent and how to verify its correctness all the way down to the C level. Just as a quick refresher on what binary search is a searching algorithm that, given a sorted sequence, determines if a given element is in the sequence. It achieves this by checking if the middle element in the sequence is equal to, less than, or greater than the element we are searching for. If it is equal, we finish our search. If it is greater than, we restrict the search to the first half. If it is less than, we restrict the search to the second half. And we repeat this until we either find it or the subsequence that we are searching on is empty. The functional correctness specification of binary search can vary depending on whether or not we want to return the index of the element or not. In this case, we do. And so, in the case that we do not find the element in the sequence, we return an index greater than the length of the sequence. To implement binary search in Cogent, we need several functions. These are a function that we will call stop that terminates the search early if we have found the element or if the element is not in the sequence. A function that we will call search that searches the current subsequence, that is, compares the middle element with the search value and restricts the subsequence accordingly. And a function that we will call binary search that does the necessary setup and formatting of the returned value. To do the actual looping and reading of elements from a sequence, we will need to import foreign data types and functions. And so we import from C arrays to represent sequences and its operations length and get. We also import repeat. With these functions, we can implement binary search. As you can see, there are several dependencies here. The search function depends on get, binary search depends on length and repeat depends on stop and search. These dependencies will determine how we compose correctness theorems. Once we have implemented binary search in Cogent, we want to know that it is correct. Moreover, we want to know that the compiled Cogent program, that is the C code, is correct. The correctness theorem would look something like this. This essentially states the same thing as the functional correctness specification of binary search, except that we have the additional assumption that the array in C is valid, and that we need to prove that when the function binary search is executed in C, it doesn't modify the array at all and the array is still valid. These parts are in red. To prove that the C implementation satisfies this theorem, we just need to compose the functional correctness theorem of the shallow embedding of binary search, assuming we have already manually proved this, and the refinement theorem from shallow to C for binary search. To obtain the refinement theorem for binary search, we simply need to compose the automatic refinement theorems generated by the compiler with our manual ones. That is, we compose the refinement theorem for binary search with length and repeat, which then requires us to compose it with stop and search, which then requires us to compose it with get. While this is definitely not a formal proof, the real one can be found on GitHub. This outlines the key steps that one would need to take to prove functional correctness down to the C level, and that this approach is fairly straightforward. To summarize, we have demonstrated a cross-language approach to software verification. We have also shown that a language can maintain its guarantees when it interoperating with another language if it uses a principled foreign function interface, and that the correctness and safety theorems of individual components can be composed to obtain a total correctness and safety theorem for the whole system. We have achieved this through a case study of a mixed system composed of safe functional language, Cogent, and an unsafe imperative language with few guarantees, C. Specifically, we have manually verified the correctness and safety of an array and general loop iterator implementation in C, and that these adhere to Cogent's foreign function interface requirements, and use these proofs to discharge proof obligations generated by the Cogent compiler when used to prove functional correctness of file system operations in previous work, thus showing that the composition of automatically and manually proved correctness and safety theorems of a Cogent-C system is straightforward. We believe this approach is likely reusable in the context of verified and certifying compilers. Thank you for listening.
Thank you, Louis. I don't see any questions in the Q&A. Are there any questions in person?
Any questions here in the room? No.
So, we did have a question from Andre on the chat. Andre asks, Is it really crucial that Cogent is not Turing complete? How is it? What would a Turing complete version of Cogent look like? I think.
So do you mean the fact that Cogent doesn't support recursion and stuff? So the reason why we don't support recursion at the moment is because it was just at that point in time, it was easier to guarantee totality because part of the refinement proofs require us to show totality of the C code. And so doing that in general is hard. There is a project in the work for adding a limited form of recursion for strictly positive types, but that's still in the works at the moment.
Okay. So it sounds like the real question, the important thing is totality, not Turing completeness.
Yeah.
Or, no, yeah. So I have a related question. What would it take if you wanted to use Cogent's FFI interface with some other language? If we didn't want to target C, what would be the, I don't know. What would be needed to support, say, programs written in a different language, or linking with programs written in a different language?
To do that, we would need to change, first of all, one of the compiler phases, the very bottom where it interfaces with C, just where it handles the calling in of stuff. There would need to be a slight tweak there. But apart from that, since all the semantics are defined just as Isabelle terms and relations and stuff, I personally don't believe it would be that hard to say add another language. It's just more of the engineering down at the bottom to sort of hook that other language in.
Okay, thanks. Are there any more? Yeah.
Last chance for questions locally? No.
Well, if not, let's thank Louis again.